about Kirchhoff laws. Okay. Earlier we have seen when the resistance is connected in parallel or in series, or in case of Ohm's law we have seen how the resistance and current is present. Now we are applying the Kirchhoff laws to that. Kirchhoff laws we are having mainly two are there, as you know that is of about we are having the current law is there and voltage law is there. Okay. Whereas in case of this current law, if you are taking current law, it is nothing but at a junction point, if you are taking at a junction point, if you are taking at the junction point here, the sum of the incoming currents has to be equal to the sum of the outgoing currents, that is. Or you can also write that as at that junction point, the algebraic sum of all the currents has to be equal to 0, that is. Maybe you are very well known of this statement here, of which at any junction point you take, whatever the incoming currents if you are taking and the outgoing currents if you are taking, then all the three currents it should be same we have to get. Or at this junction point, the sum of the algebraic sum of the currents has to be equal to 0. At this junction point we are taking. So, the sign convention we have to take is, we have to assume that all incoming currents has to be positive and all outgoing currents take that as a negative, that is. Which means the one which is coming incoming, that is taken as a positive, and the one which is leaving, that we are taking that as a negative. Okay. For example, in this case if you are taking I1, it is coming towards the junction point O. I1 I am taking that as positive, and I2 and I3 they are leaving that. So, that is why I am taking them as minus, that is minus I2 minus I3. Then according to this statement, the algebraic sum of the currents at the junction point if you are taking, that is equal to 0, or from this you can write I1 is equal to, bring this I2 this side, I3 this side. So, in another way also we can tell this Kirchhoff current law, that is, which is whatever the algebraic sum of incoming currents at the junction point is equal to the sum of outgoing currents, that is. Here the incoming current is I1 and outgoing currents are I2 and I3. So, that is why the sum of the incoming current I1 is equal to the sum of outgoing currents which are I2 and I3, that is. Like this we can write the current law for that. Okay. So, this is called Kirchhoff current law, that is, or it is also called as a junction law, that is. And we are having one more, that is, which is of we are taking for the case of voltage law, that is. Okay. When you are taking for the case of voltage law, which is the second one, according to this voltage law, when you are considering any of the closed circuits, any of the closed circuit you can take. In case of this closed circuit, what happens there is, whatever the potential difference changes you are getting inside that closed circuit, which means when you are taking two or three electronic appliances inside that, we are having, there is a change in the potential drop occurs depending on the resistance there. So, as depending on the resistance, as there is a potential drop takes place, then what happens there is, here we are having different voltages are present. But finally, this voltage drop is because of due to the main source potential difference we have, main voltage, means whatever the potential drop we are having, all that sum it has to be equal to the final voltage there. So, which means in another way we can tell that whatever the difference or whatever the changes we are getting in the potential difference, that is equal to the potential, that is the algebraic sum, it has to be equal to 0, that is. Okay. For example, if you are taking considering a circuit here, let us say for example, you are having like this, having a resistance, the potential difference here, and you are having one more resistance with another potential difference, and we are taking one more resistance here like this. Total 3 resistance we have, having R1, having R2 and R3, having the voltage V1, having the voltage V2. Like this we are having R1, R2 and R3 are there, which are arranged at the voltages. V1 is the potential difference and V2 is the another potential difference we have. Okay. Now, according to this Kirchhoff voltage law, if you are taking, or it is also called as Kirchhoff loop law, that is, loop law means where we are taking a closed loop, that is. If you are taking the junction points here, let us suppose here it is A, let it be this is B, and here it is C, let it be this is D, here let it be that is E, and here it is F if you are taking. Then according to this, let us suppose if you are taking the current passing, then let us suppose I1 is the current passing here, I2 is the current passing here, of which as that voltage negative you are having, let us suppose you are taking the current opposite direction, as the current always goes from low potential to high potential, that is. As it is going from high potential to low potential, let us suppose here the current coming is I1, here I2 and here going is I3, that is at this point. Because at this point the incoming current here we have, and at B the incoming current is there, total I1 plus I2 is added here, let it be that current is I is passing through this R3, that is. Then that current which is passing through I3 is now coming inside towards V2 again, and again I1 it is passing there, like this. For this simple circuit, now we are applying our Kirchhoff voltage law. Once again, if you see the statement there, as I said, any of the current carrying wire, if any of the closed circuit if you are taking, whatever the changes in the potential difference you are getting, or whatever the changes in the potential drops we have across any of the electronic components you got, the algebraic sum must be 0. The algebraic sum must be 0. Then if you apply here for this, for the any of the closed loop here, let us suppose if you are applying the closed loop, first one A, B, E, F, A, B, E, F and A. For this closed loop, if you are applying this Kirchhoff law here, then for A to B, we do not have any circuits are there, A to B. So, there is no change of potential difference across this one, but when you are going to B to E here, you are having a resistance is present. And remember, when you are going against the resistance here, then that current, whatever the current you are taking, as you are going against the direction of current, the resistance try to oppose and you are also going against the current, then we have to take that as a positive, that is, which means plus I2 R2 we are taking. And next we are having a voltage source is there, and that voltage source actually we are having from high potential region to low potential region. So, that is why here we have to take that as minus, that is, as we are going from high potential to low potential, that is. And when you are coming across E to F, we do not have any of the potential drops are coming there, and after that we are having F2 again back to A we have. Okay. While going from F to A, again we are having one more resistance is present. That resistance value actually we are going against the direction of the current, and so that here we have to add that resistance, that is, which is plus I R3 we are taking. Then finally, from A, B, E, F, A to the complete circuit, whatever the sum we are having, that potential difference across that, which is I2 R2 minus V2 plus I R3, all this algebraic sum is equal to 0. This is nothing but called as this Kirchhoff voltage law, that is. From this actually if you observe, we can write that as minus V2 coming this side becomes plus V2 is equal to I1 of R2, I2 of R2 plus I of R3, that is. Because that R2 and R3 if you take, those are in a series, that is. Okay, so that's why you got V2 is equal to I2 R2 plus I R3, that is. This is called Kirchhoff voltage law, that is. Okay. So, one is the current law and another one is for voltage law, that is. But actually the questions which we are getting on this current law and this voltage law is, in case of current law if you observe, whatever the current you are having at the junction point here, incoming is equal to outgoing, means there is no charge which is the current you are taking, as there is no current is present at that junction point, of which the algebraic sum is becoming a 0 here, means incoming current is equal to outgoing current. And we know that current is nothing but the rate of flow of charge. As it is about the rate of flow of charge is present here, the incoming current is equal to outgoing current, means whatever the number of charges you are getting inside to that junction point here, the same number of charges are leaving the junction point. So, that is why this Kirchhoff current law, actually we call that it is the consequence of conservation of charge, that is, this Kirchhoff first law, it is about consequence of conservation of charge. Okay. In exams, they are asking, the competitive exams, they are asking about like this only. This Kirchhoff voltage law or Kirchhoff current law is about which conservation that is. So, if you are taking about the considering the current law here, which is the loop law, which is called the junction law here, it is about the conservation of charge we have, because the incoming charge is equal to outgoing charge that is. So, that is why it is called as conservation of charge. Whereas, if you are coming to the case of the voltage law here, as the voltage law tells, if there is the algebraic sum of difference in the potentials, if you are taking in a closed circuit across different electronic components, if you take, their algebraic sum is becoming 0, which means that whatever the potential difference changes you are getting, means change in the potential difference. We know that change in the potential difference is nothing but called as work done on unit charge. Whatever the changes in the work done you are getting is equal to 0, which means the work done always remains constant. So, means as the work done remains constant, that work is nothing but called the energy here. So, that is why here the energy remains constant. So, that is why this Kirchhoff voltage law, actually that is a consequence of energy we have, whereas Kirchhoff current law, that is of the consequence of conservation of charge, and Kirchhoff voltage law, that is about the conservation of we are having energy is present. Like this, both the laws are of conservation of charge and conservation of voltage law we have. So, before going to see any of the numericals about this Kirchhoff laws, at first we have to remember about its sign conventions here. Okay? Then in the case of first one, which is a easy one, which is the current law, if you are taking all incoming currents, we are taking that as positive. Means when you are taking at a junction point, when the current is coming, take that as a positive current, that is. And whenever if you are taking any of the current which is leaving the circuit or leaving that junction point here, that current we are taking that as minus, that is. Okay? So, all incoming we have to take that as positive, all outgoing we have to take that as negative, that is. That is the sign convention we are following for the case of Kirchhoff current law, that is. And when come to the case of Kirchhoff second law, which is the voltage law, if you are taking, very important one, when you are going across any of the electronic appliance there, when you are having the resistance is present particularly and a voltage drop, voltage is present here, mainly we have to see if you are in the direction of current is there, if you are in the direction of current and if you are having a resistance is present across that, then how to take that is, if you are in the direction of current taking, then we have to take minus R, that is, which means I of minus R is the potential drop across that. Okay? V is equal to I into minus R, which means that is taken as minus I R. Okay? Now, if you are going against the current here, means if the direction of current is opposite to that, if you are taking, means like this if you are taking, then going from A to B and here also going from A to B, then here you have to take, as you are going against the direction of current and resistance also opposing the current, here you can take V value as I of plus R we have to take, if current is I, then it becomes V plus I R, that is. Okay, like this, plus V I R, that is, V is equal to I R, that is. Okay. Like this, if you are going from opposite to the direction of current and in the direction of current, the resistance values are like this. And for suppose if you are having a voltage is coming there across that, then how to take that voltage case is, if you are taking going from A to B, if a voltage source is there like this, then if you are going from high potential to low potential, here A to B means going from high potential to low potential. In this case, V is taken as a negative, that is, because we are starting from a high potential region and we are slowly going towards the low potential region, that is. So, that is why V we have to take that as a negative, that is. Whereas, in case of if you are taking low to high potential, that is, means going from A towards B here, then in this case as you are going from A to B, low potential region to high potential region, then V is taken as positive here, like this. This is of minus V, that is, and here we have to take plus V, that is, if V is the voltage is present. Like this, depending on the given direction you are going there, while taking that closed circuit or closed loop, we have to change the sign convention here. If you are going against the direction of resistance, we have to take that as positive. If you are going in the direction of resistance here, if a current is there, then we have to take minus IR1 and IR, that is, and here if you are taking for the case of A to B, going from high potential region to low potential region, we are taking that as negative, and if you are going from low potential region to high potential region, that is taken as positive here. So, these are the sign conventions we have to follow when you are going to apply these Kirchhoff laws. Now, based on these Kirchhoff laws, now we will see a small numerical on that. Okay. So, here in the given circuit there, we have to find the current drawn from 12 volts battery, that is, which is here we are having a 12 volts battery is there. To the 12 volts battery, we are having a 3 ohm resistance, and one more battery is also there, which is of 5 volts is there, having 2 ohms, that is, and here we are having 4 ohms is present. Total 3 resistance are there, and 2 potential sources we have, 2 voltage sources also we have. Okay. Now, at first, while taking this direction of the current, if you are taking, as it is of 12 volts battery, we are having more potential difference is present here, more potential is there. Let us suppose the current here it is started, and at this junction point, now at first if you take the junction points here, let us suppose this is A, B, C, D, E and F. Then at the junction point F here, the current is incoming here. The current actually it is at this junction point, it goes in 2 different parts. One is going up, another one is going down, that is, means through 4 ohms resistance, the current passing is I2 there, and it is coming to C here, and again back here it is passing there, of which here it is now through 2 ohms here, the current is coming inside, let it be, that is I1, and it is coming down here, and again at C, both the currents are passing as I, that is. Okay. So, means finally through the 12 volts battery, that is, we are having the current passing is I is the current passing there. Now, what we have to find is what is that current passing through 12 volts battery. Now, while taking this circuit resistance here, as I said, in the case of that Kirchhoff voltage law, if you apply, now we are having total 2 closed loops we have. One is this one, which is A, B, F, C, and another one we are having F, E, D, C, F. So, total 2 circuits we have. One is A, B, C, F and back to A. This is the first one we have. Now, if you apply the Kirchhoff law to the first one, A, B, C, F, A, then A to B, B to C, C to F and F to A for the first case. Now, while going from A to B, first if you are taking A towards B, if you are going, then we are having coming across a potential source there, voltage source, and coming across a resistance here. When you are crossing over that voltage source, according to the sign conventions given, here actually we are going there from high potential region to low potential region. So, means the voltage value we have to take is minus V, that is, where that voltage is given as 5 volts, that is. So, which we consider that as minus 5, that is, as we are going from high to low. After that, we are having a resistance is present, which is of 2 ohm resistance is there, whereas we are going in the direction of current and the resistance actually oppose that. So, that is why we have to take that as minus, that is, and the current passing through that resistance is I1 is the current. So, that is why minus I1, and the current passing through that, the resistance there is 2 ohms, that is. So, IR, that is, which is I1 into R value given as 2, that is. Now, that is about for A to B case. Now, while going from B to C, we do not have any potential drops there. So, that is why no zero potential drop, and while coming from C to F, we are having C to F. Here at C to F, the current passing through that circuit is I, that is, and we are coming across a resistance here which is of 3 ohms, and we are coming in the direction of current here. So, that is why through that 3 ohms we have to take minus 3, that is, so which is minus 3 I we have to take. And it is coming across a voltage source here which is of 12 volts, that is, and not only that, we are going from the current from low potential region to high potential region, that is, which is taken as plus 12, that is, minus 3I plus 12, that is. Okay. Now, on taking that complete circuit there are, because for F to A we do not have any circuits are present here. So, that is why the potential drop across this one is also equal to 0, that is. Then the final for A, B, C, F, A, we are getting finally minus 5, minus I1 into 2 and minus 3I plus 12. That algebraic sum of all these potential differences is equal to 0 according to our Kirchhoff voltage law, that is. Then if you are having minus 5 plus 12, which becomes 7, and minus 3I we have, and 2 into minus I1 we have, which is minus 2I1 minus 3I plus 7 is equal to 0. Or we can also write that as 2I1 plus 3I minus 7 is equal to 0. Let it be, this is equation 1. Now come to the second case, which is the second loop we are taking. While taking the second loop, if we are taking starting from F, C, D, E, F if you are taking, means again it's the second closed circuit we are taking, which is this time F, C, D, E, F, like this, F, C, D, E, F, that is coming back to F. Then while going from F to C if you are taking, we are going from high potential region to low potential region, and not only that, the current passing in that circuit, in that line is I is the current. As we are going from positive to negative, then it becomes minus, that is, which is minus 12, which is for the case of FC if you are taking, then minus 12, that is. And when you come across the resistance here, as we are going against the direction of current, then the resistance value it is taken as positive, that is. So that's why in this case we are having plus 3I we have. And while going from C to D we don't have any potential drops there. And after that, if you are going to D to E, we are having only one resistance we are having that. So that, and you are going against the direction of current here. So that's why that resistance value we have to take that as a positive, that is. And we are having I2 is the current passing in that D to E, that is. And coming back to E to F, again we are not having any of the potential drops across that one. So that's why here the total potential difference across the points, if you see F to C to D to E to F, then finally we got minus 12 plus 3I plus 4I2 is equal to 0 we got. Or from this you can also write that as, which is 3I plus 4I2 minus 12 is equal to 0. This is our second equation we got. Now we got both the equations, 2I1 plus 3I minus 7 is equal to 0, or 3I plus 4I2 minus 12 is equal to 0. And not only that, we know that I1, I2 are nothing but equal to the sum of that I we are taking, which is I is equal to I1 plus I2. I is equal to I1 plus I2 you can take. Here I is equal to I1 plus I2. Then if you substitute any one of the value here, I1, let us say for example, if you are taking I1 value, then from this you can write I is equal to I minus I2, that is. Then if you substitute I is equal to I minus I2, in the first equation if you see, 2 of I1 is equal to I minus I2 we have plus 3I minus 7 is equal to 0. Then if you multiply that, then it becomes 2 into I, 2I minus 2 into I2, 2I2 plus 3I minus 7 is equal to 0, like this. So finally we got the two equations here, which is of 2I minus, here of 2I plus 3I, total it becomes 5I, total it becomes 5I minus 2I2 and minus 7 is there, which is minus 7 is equal to 0, that is the first equation. And the second equation we got, which is of 3I plus 4I2 minus 12 is equal to 0. So finally these two equations we got after changing that equation here, all are in now in terms of I and I2 is there. So what we need is I value. So we have to eliminate that I2 value here. And you already seen that here we are having 4 I2 is there and here we are having 2 I2 is there. So means if you multiply this first equation with 2 and if you add that, then that I2 can be eliminated here. So that's why what I am doing is, if you consider this is a 1 and this is a 2, now I am adding second equation plus 2 times the first equation, that is I am multiplying with 2 that first equation, so that it becomes 10I minus 4I2 minus 14 is equal to 0. And the second equation, which is 3I and plus 4I2 and here minus 12 is equal to 0. Then if you add that 10I plus 3I, 13I, plus 4 and minus 4 get cancelled, and here we are having minus 26 is equal to 0. Then 13I is equal to 26, then I becomes 26 by 13, which is 2 amperes we are getting. So, the current passing through that 12 volts battery, it is of the current, it is equal to 2 amperes, that is the total current passing through the 12 volts battery or in the circuit. Okay. Like this, we can solve the equation by using this Kirchhoff voltage law, applying for the case of two closed loops we have. Okay. Like this, separately we have to take following the sign conventions A to B to C to F to A and F to C, C to D, D to E and E to F. Like this, we can solve any type of the closed circuit there by using this voltage law. The power, which is electric power, we are taking. So, again based on electric power also, we are having number of questions they are asking. For example, electric power. We already know that power is nothing but the rate of doing work. Actually, when come to the case of rate of doing work here, this work is done by the electrical energy here, which is doing on each charge, that is. As we know that power is equal to work by time. Here work means nothing but here we are taking W is equal to VQ, that is, which is the potential difference here we are applying across the unit charge here, which is VQ by T, that is. So, from this we can write as Q by T, it is equal to I, that is. Then power P is equal to V of I, that is. So, the formula to find the power, when you are maintaining some voltage potential difference V there and current I is passing through that, then power given by P is equal to V into I. But actually from Ohm's law we know that as V is equal to IR, then if you substitute V is equal to IR in that, then IR of I, it becomes P is equal to I square R, that is. So, this is the formula if you are having the current and resistance is present in the given circuit there. So, P is equal to I square R. And after that we are having P is equal to, if you apply there, we know that as V is equal to IR, we can also substitute R is equal to, from that V by I also we can substitute. Then as P is equal to VI, then we are applying as I is equal to V by R, that is, then we can also apply V by R in place of I, that is, because V is equal to IR, that is. Then P is equal to, then finally it becomes V square by R. Like this, depending on the given problem here, the electric power we can write that as P is equal to V into I, voltage and current relation, and P is equal to I square R, I and R relation, and P is equal to V square by R, P and R in terms of voltage and resistance here. So, means any of the electronic appliances if you are taking, they are having their wattage is present, the power, electric power is present there. If you are connected in series or if you are connecting in the parallel, it may depend on the resistance we are taking. For example, if all the bulbs are connected in series, in case of series connection, we are having that current remains the same. So, that power actually depends directly proportional to R, that is, which means the power given here, it is directly proportional to the resistance of the bulb inside that. So, that what happens there is, if you are arranging the number of bulbs there, gradually all are in series. If all are in series, gradually what happens there is resistance increases. So, the power delivered is also more in that case. Then we have to add all P1 plus P2 plus P3 like that. And for suppose if you are arranging in terms of the voltage here, which is you are taking for the case of a parallel connection, then P and R, that is of inversely proportional to each other here. So, as those are of inversely proportional here, so as the voltage here it is resistive, as the voltage remains the same, then the power and resistance both are inversely proportional to each other. That is also like we seen in case of V is equal to IR there. Okay. So, as if the voltage remains same, then power is directly proportional to the current we have. Like that, depending on the given conditions, for example here, if V is constant in case of series, in case of parallel, if you take series case, and in case of parallel case if you are taking, in case of series, then I remains constant, I is equal to constant, that is. Then as I is equal to constant here, then the power delivered is directly proportional to the voltage here in case of series. And not only that, here the power is directly proportional to the resistance, that is. Okay. And when come to the case of the parallel connection, in this case, as the voltage remains constant here, then in the first case here, that power, it is directly proportional to how much is the current drawn there. And in case of the second one, if you are taking, that is inversely proportional to the resistance, that is, okay, like this. So when connected in series, when connected in parallel, the electric power varies depending on the condition we are taking, whether they are arranged in series or they are arranged in parallel. So depending on that parallel and series connection, the power delivered is changing here. So based on this also, we are having number of questions they are asking. Now, just like the power we seen, now we are having the same thing for the case of electrical energy is also present, because as power is equal to rate of doing work by time, then we are taking that work done as energy here, because that work done is done by the electrical energy, that consumption of electrical energy only doing the work here. So that's why we can also write P is equal to energy by time also. Whatever the energy consumption we have per second, that only we call that as electric power. Or we are using that electrical energy is equal to power into time, that is. Okay. Now, if you are taking for the case of this electrical energy, we are having different forms are there, because we know having the power in terms of voltage and I is there, I and R is there, and V and R is there. If you substitute that values here, this electrical energy, we can also write that as power into time, where power, if you are taking the voltage and current is present, we can take that as V into I into T, that is, this is one formula. And if you are using the formula P is equal to I square R, then electrical energy becomes as power is equal to I square R into T, that is I square R T. Means more and more time if you are passing the current there, more and more electrical energy is consumed there. And whereas if you are taking electrical energy for the another case, which is P is equal to V square by R, if you are using, then V square by R into T, that is. Again, even for this electrical energy also, it varies with the series and parallel connection here. For example, if you are taking for the case of a series connection, the current remains same and the voltage continuously changes here. So depending on the voltage, this electrical energy is consumed here. And if you are taking for the case of E is equal to I square RT, as it is in series, I remains constant here. So that's why this E depend on the resistance you are taking. And when come to the case of if voltage remains same there, then E is equal to, as the voltage remains same, that electrical energy is inversely proportional to the resistance we are taking. And if you are taking for the case of E is equal to Vi into T, as electrical energy, as the V voltage remains a constant here, that electrical energy is directly proportional to the current we have. So like this, depending upon given there, the whether it is a power or electrical energy, we are having a different relations are present between V, I and R. So given question is, which of the following has high resistance, that is, when voltage is equal to 240 volts you are taking and I is equal to 5 amperes you are taking here. Okay. Now, of the given here, the voltage it is of 240 volts, that is, and the current I is given as 5 amperes, that is. And the options given here are option A 60 watts, B given 100 watts, and C given 40 watts there, and option D given 80 watts, that is. Actually, which of the following has high resistance we are taking, means the resistance value has to be more. Of the given, we know that P is equal to V into I, or the power formulas we have V square by R, and P is equal to I square R if you see. Now, of all these cases here, the second one we have, when you are taking about the voltage here, as the voltage is fixed, which is of 240 volts, that is, then as the voltage is fixed, the power and the resistance both are inversely proportional to each other, as P is inversely proportional to R, that is. Okay. As P is inversely proportional to the R, having more power always gives you less resistance we have for that, and having less resistance we are having more power is there for that. And of the given options, as we are having we need the highest resistance here, which is the maximum resistance, means R value we need to be more. So, that is why the power we have to take should be less. Of the given options, if you see 60, 100, 40 and 80 there, we are having the less power, it is meant for 40 watts here. So, that is why the correct option, it is going to be for 40 watts, that is. Okay. Or if you want to find out how much is the resistance you are having in case of that is, as we know that P is equal to V square by R, as P is equal to V square by R if you are taking, then the highest resistance if you are finding, then if you see that R value is equal to V square by P, if you are checking for the first one, it becomes as V square, the complete voltage if you are drawing, which is 240 square by, and the voltage, the power we are having is 60, which is 4 times 240, that is. And if you are taking for the second one, and again V square by R, which is 240 into 240 by, second case it is of 100, we are having the 24 square is there, and where we are having for the third case, which is our answer, V square, which is 240 into 240 by 40 if you are taking, then 6 into 240, that is. And for the fourth case if you are taking, which is of 80 watts, that is, which is 240 into 240 by 80 we have to take. Then 240 into 240 by 80, which is of 3 into 240 we have. Here we are having 4 into 240 and here 24 square and 6 into 240 and 3 into 240 if you check. Of all these cases, the third one, which is 6 into 240, we are having the maximum value is present. So, that is why in this case here, as the resistance more it is for, when the power drawn it is about 40 watts is there, then the resistance value is more. So, like that we can relate the resistance with respect to the power, because here the power and resistance both are inversely proportional to each other for the given fixed value of the voltage we have. Okay. Now, if you go to the next one, here we are having the resultant resistance of 4 watts and 6 watts when they are connected in parallel combination is given. Actually, when they are in parallel combination, the voltage remains the same for that. So, then what happens there is, as P is equal to V square by R, as that voltage remains same, then power is inversely proportional to resistance, that is. As the power it is of V is into I, that is. So, as power we can write that as V into I is inversely proportional to R. As V already it is a constant, I is inversely proportional to R, that is. So, which means it is just like related to our Ohm's law here, which is V is equal to IR case, where the voltage remains the same here and I and R both are inversely proportional to each other. So, it is just like our resistance which is connected in parallel combination, that is. Okay. So, there if you do that, then the resistance value it becomes as it is of the resistance in parallel case, we are having 1 by 4 plus 1 by 6 if you are taking, because both are related inversely proportional same as the resistance we have, then 1 by 4 plus 1 by 6, then resistance in parallel it becomes here the LCM it is of, we are having 12 we are having the LCM there, 4 3s and 6 2s, which is 5 by 12, that is. Our RP value from this we will get 12 by 5. Whereas the 12 by 5 it is equal to 2.4, that is. So, as it is directly proportional just like the resistance we have for the parallel, then what happens there is, even in the case of that parallel combination also, here 4 ohms, 4 watts and 6 watts, they are connected again. If you are connected that in parallel, then we are getting a wattage of 2.4 wattage we will get. So, the answer is going to be 2.4 wattage. Like this, we can relate that power to the resistance here, or we can relate that power to the resistance when connected in series also. For the same question, if they ask in case of a series combination, if they give, then directly just like the resistance, as we are adding both, because in that case the current remains the same there, then power P is equal to I square R we have. As the I is constant here, then P is directly proportional to the resistance. As the resistance is added there, here also we are adding the resistance, so that the resistance is increasing, so that the power also increases. Finally, it becomes 4 watts plus 6 watts, it becomes total 10 watts, that is, if you are using a series connection. But in our problem, it is given the combination is a parallel combination, that is. So, that is why the final power, as P is inversely proportional to the resistance here, as it is decreasing, that is why here the power also decreases to 2.4 watts, that is. Now, we will see one more question, this time on electrical energy question we will see. If each tube light draws 40 watts on the average 5 tubelights are used for 6 hours in a day. Then find the consumption of electrical energy in all the 30 days here. Okay. Now, here we are finding the electrical energy, that is, and power is given there, where that power is equal to 40 watts, that is. Then if each tube light we are having a 40 watts there. So, each tube light actually we are having 40 watts they are consuming. So, that total number of bulbs we are having, that is 5 in number we have. Okay. So, the number of tube lights we have, number of tube lights, that is of total 5 we have, and each used for a time of 6 hours, that is. Then the time is also given, which is of 6 hours, that is. Then in a day if you are using for 6 hours, then for a month which is of 30 days, then for 30 days the consumption time becomes 6 into 30, that is, which is of 180 hours is required there. Then if you are using for 180 hours in a month there, which is of 30 days, and we are using the wattage of 40 watts there in each case, then how much we are getting that electrical energy is, we know that the electrical energy is nothing but equal to power into time, that is. That power actually we have, that is of 40, that is, but we are having each tube light, that is of having drawing 40 watts, that is, whereas as we are using 5 in number there, then that each one 40 watts into 5, and the total time consumed here, it is of 180 hours, that is. So, 180 watt hour, that is. Okay. Then 40 into 5 into 180 watt hour, that is. Then if you multiply that, we are getting 40 into 5, which is 200 into 180 watt hour, that is, or we can also write that as 36,000 watt hours, that is. Okay. Then if you are taking that 1000, then the electrical energy becomes 36 kilowatt hour. So, means that electrical energy consumed in a month of 30 days, that is equal to 36 kilowatt hours. That 1 kilowatt hour only we call that as 1 unit of electrical energy. 1 kilowatt hour is 1 unit of electrical energy, that is. So, that as 1 kilowatt hour is equal to 1 unit of electrical energy, as we got here, consumption of electrical energy is equal to 36 kilowatt hour, that is. So, that we are consuming 36 units of electrical energy in all these 30 days. Like that, when a power is given for the given electronic appliance there, of which how much is the time it is consumed there, how much is the time we are using that electronic appliances, we can find how much is the electrical energy we are consuming in all those days by using the formula P electrical energy is equal to power into time. Actually, in this electromagnetic induction, magnetic flux is nothing but here whatever the number of magnetic lines of forces passing over an area, that only we call that as magnetic flux. Magnetic flux actually it is represented with the letter phi. Okay. So, phi means the magnetic flux, that is. Now, this magnetic flux in the exam they are asking about particularly about its units. Magnetic flux actually it is having the units of Weber, that is. Okay, magnetic flux it is called Weber, that is. Okay. Now, magnetic flux is nothing but the number of magnetic lines of forces passing over an area, that we call that as magnetic flux. Now, actually this magnetic flux depends on here how the magnetic lines of forces are passing over that area here. If you take the formula here, magnetic flux formula is phi is equal to B cross A, that is, or B dot A, that is. Okay. So, magnetic flux phi is equal to B dot A or B A, that is. Okay. Then, when you are taking that B A here, now if it is going perpendicular to the area here, always the flux is maximum we are getting. But whereas if you are taking that going parallel there, then we are getting a minimum flux here. Okay. So, that is why here that flux per unit area means the number of magnetic lines passing over unit area, that only we call that as magnetic field strength, which is called B, magnetic field strength, where that magnetic field strength B is equal to phi by A. Then if you are taking the units for the case of B, the units are Weber, which is for the phi, and area it is of meter square, Weber per meter square, or it is also called as Tesla, that is also called as Tesla. Okay. The magnetic flux per unit area, we call that as a magnetic field strength there, and whereas that magnetic flux is nothing but the number of lines passing, the number of magnetic lines passing over an area, that we call that as a magnetic flux. That is, that magnetic flux formula is B dot A, that is, or simply BA, that is. But remember, if you are taking these magnetic lines of forces, if they are crossing the area perpendicular to each other like this, then what happens there is, here as the area it is having the direction normal we are taking, which gives you the direction, the angle between the magnetic lines and that area, it is of 0 degrees we have, as both are going parallel to each other here, then we are having the magnetic flux here, it is becoming a maximum we have. But if it is making some angle, if we are taking, which means that magnetic flux is making some angle area we are taking, instead of taking perpendicular, if you are taking making some angle there with the magnetic lines, let it be that is theta if you are taking, then here the flux changes comes here, and here the flux formula becomes phi is equal to BA cos theta, that is, it is of BA cos theta. When they are going parallel to each other, as I said, here the angle between the magnetic line and the area, that is of 0 degrees we have. So, that is why cos 0 becomes, it is of a maximum we have. So, means this is maximum when B and A are perpendicular to each other. B means the magnetic lines of forces which are passing there, and A means the area you are taking. When both are perpendicular to each other, we are having a maximum flux is coming. But if you are taking that area, if it is taken parallel to that, means the angle between the normal to that one, it becomes 90 degrees, then cos theta value we have to take that as 90 degrees. So, there in that case we are having cos 90 value, which is minimum. So, the flux value is becoming minimum when you are taking B and A both are parallel to each other. So, most of the cases on the flux, they are asking mainly about 3 questions here. One is about the SI unit of this magnetic flux, of which we are taking that as Weber, and the SI unit of this magnetic field strength, that magnetic field strength, its SI unit is Weber per meter square, or it is also called as Tesla, that is. And they are asking about when we are having a maximum flux is there, or when we have minimum flux is present. Maximum flux we are getting that when you are taking the magnetic lines of forces are passing perpendicular to the area, if you take there, we are having the maximum flux is there. And when you are taking, if the magnetic lines of forces and the area here, area of cross section, if both are parallel to each other, in that case also we are having the minimum flux takes place. And if you want to generalize the formula here, the flux is given by phi is equal to BA cos theta. Now, we will see this electromagnetic induction law, that is. See, according to our Oersted activity, we know that whenever if you are passing the current here, around that current carrying wire, we are having a magnetic field is coming around that one. Okay. As you already know about this electromagnetic induction, of which we are getting the magnetic fields are coming because of due to a moving charge. But here the important thing we have to remember is, whenever the charge is at rest, there is no magnetic field is present around that. But once the charge is in motion, we are getting a magnetic force is acting on that one. So, based on this also we are having number of questions are there, of which some of that you can take. Here we know that whatever the force it is acting, that force acting is directly proportional to how much is the magnetic field is present around that. F is directly proportional to the B value here. And not only that, here whatever the velocity we are giving for the charge, even that also affects the force acting on that. So, here F is directly proportional to the velocity of the charge it is moving, and also equal to the magnitude of the charge you are taking. If you are taking more and more amount of charge, then the force acting on that also increases here. So, F is directly proportional to Q also here. Like this, the whatever the force acting, the magnetic force which is acting on that charge, when you are exposed that inside a magnetic field here, then that force acting is directly proportional to B, Q and V, that is, which is F is equal to BQV, if you are taking that constant as unit. then as F is equal to BQV, which means when you are taking any of the electric charge inside a magnetic field here, inside a uniform magnetic field here, then it applies some force on this charge. That force only it is equal to BQV, that is. And if you want to generalize that formula, instead of taking perpendicular to the field, then if you generalize that formula, then it becomes F is equal to BQV sin theta, that is. That sin theta, it is the angle between, where theta is the angle between B and V, that is. That is the angle between the magnetic force acting there and in which direction that velocity of the charge it is moving there. That is the direction of the velocity and the direction of the magnetic field we have. Okay. Then as F is equal to BQV sin theta, here the question they are asking about the direction of the charge it is moving when this force is acting. Okay. Here only the important one, we have to apply the right hand rule here. Okay. Actually we can apply some other laws also there, but mainly here if you are taking the magnetic field which is going perpendicular here, that charge, then we have to apply this right hand rule here. So according to this right hand rule, if you remember that here always while taking the right hand rule, in which direction we are having the magnetic field is present, that B value, that magnetic field direction, always we have to use a right hand there if you are taking a charge of a positive one, and you have to use the middle finger to represent the direction of the magnetic field there. And this forefinger or this index finger we have to use for the case of if there is a direction of the velocity is present for the charge, in that direction we have to use this forefinger here. Then this thumb gives you the direction of the force. So when these two are arranged perpendicular to each other, then this thumb which is taken perpendicular to the plane of both here B and V, that gives you the direction of the force here. So based on this only we are having more number of questions are asking, that is. For example, if the question given is like this, if you are taking a charge which is entering into a plane like this, let us suppose we are having a magnetic field is present such that towards downwards we are having a north pole is present, upwards we are having a south pole is present, and we are having that charge it is present perpendicular to the N and S there, which is of we are having that magnetic force is acting here, it is of maximum we have. As the force acting is maximum we have and the velocity it is going there perpendicular to the field acting, then how we can take that is, as I said, that middle finger always represent about the direction of the force here, and those magnetic lines of forces are towards from north pole to the south pole, which is going upwards we have. So that's why that middle finger we have to take in the upward direction here. This middle finger we have to take in the upward direction, and the direction of the charge if you are taking, it is going towards in this direction towards the right side here. So that's why how to take that field is like this we have to take, of which the direction of the field we are taking that is upwards, and here this charge actually it is moving towards the right side here like this. Then the force acting here, the thumb represents out of the plane here from the board like this it is. So that's why here in this case the force acting is outside here. So means if the charge is coming here inside that, then because of due to that force is acting in the upward direction, slowly it takes a turn towards outside the plane here. Like this we are having a number of questions they are asking about the direction of force acting on a charge. That into the plane always it represents with cross mark, that is, which means the magnetic lines of forces are into the plane, that is. Like this the magnetic lines are passing inside, and out of the plane we represent that with a dot here, which is dot. Okay. This dot represents the magnetic lines of forces are coming outside here like this. Okay. Now in case of this, taking the considering of into the plane and outside the plane, how the magnetic force is acting on the charge we are finding. For example, in this case if the charge is going upwards like this, then and the current the magnetic field it is acting is inside there like this, means the magnetic lines are going inside and the charge is going upwards, then the angle between them becomes 90 degrees, and again there is a chance of applying the maximum force is acting on that one. As the charge is going upwards, then the direction of the forefinger we have to take that in the upward direction, whereas this middle finger which is of we have to take into the plane, that is, which means like this we have to take. So that when you are arranging that going upwards here and this middle finger into the plane here, which is the magnetic field acting, then towards me the force is acting. Means once the charge enter into the field here going upwards, it is taking a turn, left turn here. Means this charge which started coming inside slowly deviates towards the left side, because the force acting on the thumb is towards left side, that's why the charge is taking a turn towards the left side, that is. Whereas if you are taking, if the force acting is the magnetic force, magnetic field is acting, which is taken out of the plane, if you are taking out of the plane means we have to take this middle finger out of the plane, that is. And again the charge, if it is going upwards, if you are taking like this. Now again if the charge is going upwards, again the force acting there is upwards we have, but this time we are taking the field which is going out of the plane here, like this we are taking out, and the charge is going up and the force acting is towards the right side here. So that's why in this case the force acting here on the charge as is towards right side here, now it is taking the turn towards the right side, like this. So depending on the direction of the magnetic field is present, there is a change in the direction of the movement of the charge we have, and there is a change in the force acting. Like this, by applying the right hand rule, we are having the number of questions or acting, number of questions they are asking on this. Okay, not only for the case of charge, even you can apply even for the case of current carrying wire also the same formula, that is. Only thing is here we are having the small change in the formula, of which if there is a charge is given, we use the formula F is equal to BQV, and you know that when you are using the current carrying wire there, then it becomes the same formula becomes BIL, that is. Okay, where B is again the magnetic field strength here, and I is the current passing there, and L is the length of the conducting wire you are taking. Okay, so that is about the right hand rule and how they are asking the questions there. Now in the same way, another way they are asking the questions about the directions only, which is about when you are having a current carrying wire is present, or when you are having a current is flowing there, then around that how the magnetic force is acting, in which direction that magnetic lines of forces are present, like that one more question they are asking. Okay. Now when you are taking the case of the magnetic lines of forces, if you want to find the direction here by using this right hand thumb rule, we can find that one. According to this Maxwell right hand thumb rule, when you are taking the case of any of the straight conducting wire, if you are using that, then always point in which direction the current is flowing, that direction we have to use the thumb, and you are holding that straight conducting wire with your curling fingers, then the curling fingers are nothing but gives you the direction of the magnetic lines of forces there. So which means if in this direction the current is going, then I am curling the fingers like this. So the magnetic lines of forces are around that like this. And suppose if you are taking the current carrying wire is coming out of the plane like this, then we have to take that as it is coming outside, we have to curl our fingers to hold that one in this direction. So that's why here the magnetic lines of forces are acting in anti-clockwise direction. So means when the current carrying wire, if it is coming out of the plane, then magnetic lines of forces present around that are like anti-clockwise direction. If you are taking the same case, if it is into the plane, then the magnetic lines of forces are coming in the clockwise direction, we have to hold it. So means here in this case we have to take the clockwise direction. So by using this right hand rule, we can find the right hand thumb rule, we can find the magnetic lines of forces direction around a current carrying wire. Now like this we can use for the case of if you are using a straight conducting wire you can take, or even for the case of a circular wire you can take, or even in case of a solenoid also you can take. But when you are asking for the case of the solenoid here, most of the cases that solenoid, these magnetic lines of forces behaves just like the bar magnet here. So that's why sometimes they are asking the question that the magnetic field around a solenoid,